Okay, another fun example. Are these boiling? Okay, I have lemonade cans. I have a little bit of water in them, and they've been heating up for a while now, and they are currently boiling. The water is. So I'm going to take the can, and I'm going to put it into this bucket of ice water. This happens quickly. That's why I do too. Actually, because it's fun too. So. No longer the original shape. So what's happening is with the water boiling, the water vapor is pushing the air molecules out of the can. You got that? When I take the can and invert it into ice water, well, the cold temperature causes that water vapor to condense back to liquid water. The liquid water only took up that much space in the can. The water vapor took up the whole space of the can. So when it condenses back to liquid water, that leaves a whole volume of the can with nearly nothing in it. If it has nearly nothing in it, then the pressure in there is very small. The pressure outside is still whatever atmospheric pressure happens to be here. And so the pressure outside is bigger than the pressure inside. In this case, the material that the can is made of is not strong enough to withstand that pressure difference. And that's why it implodes. If the materials aren't strong enough, then that pressure difference causes it to implode. Okay? I have a picture in my office of one of those big oil tanker cars, the train cars, that imploded. Basically, nice steam bath to try to clean it out on a nice cold day. Sealed it up before it cooled off. The whole sucker is just crushed.
Is the space station made out of some material that keeps it from exploding?
Yes. So the space station, airplanes, it's the same thing. The space station would just be more dramatic. Inside an airplane, inside the space station, you have it pressurized so that you can breathe normal, move around normally. Outside the space station, pretty close to zero pressure. So there is a net pressure outwards in terms of on the walls. But the walls themselves, the material that they're made of, the way they're connected together, it is strong enough to withstand that pressure difference. And therefore it doesn't explode. Airplanes are the same way. Okay, the cabin's pressurized so that we can breathe normally. So inside has a greater pressure than outside. Submarines are just opposite. Submarines, the pressure is greater outside because they're deep in the ocean. They have the weight of all that ocean above them. And inside is normal atmospheric pressure. So submarines would risk imploding like this, whereas the space station and airplanes risk exploding.
So how does the spacesuit work?
I'm not exactly sure. With the spacesuit, I imagine they just flow air through it to maintain the pressure, is my guess. But they are really worried to make sure they don't get any sort of tears or anything in their spacesuits. If you've seen, the planetarium has a movie right now, the Hubble 3D, and they actually talk about how they got the Hubble into space and everything, and they talk a little bit about how they have to be really careful because they were out repairing the Hubble. They have to make sure they don't snag their suits on anything. They have to be really conscientious about that to make sure that they don't cause themselves harm.
I think that they have multiple layers.
Oh, I'm sure they have, yeah. I'm sure they have multiple layers as well. Was there another question? Okay, so pressure. Couple things with pressure. If you exert an additional pressure on a fluid, that pressure is transmitted uniformly through the fluid. An example, a hydraulic lift is a good example. I guess I don't need this one. This is a ghetto version of a hydraulic lift. Basically, there's just air in here. There used to be water, but it evaporated. If I exert an additional pressure, so I'm going to apply a force, that's the area. So the force over the area exerts a pressure, and that pressure is transmitted down to the air in here. As I push on this, the other side goes up. And that's because the pressure is transmitted uniformly throughout the entire air that's in there. So the pressure ends up pushing up on this side. But notice, I don't know if you noticed or not, this moved a lot farther than that did. Much farther distance. But yeah, same volume. Exactly right. This one's harder to push than this one. I don't have to push nearly as hard on the small one as I do on the big one to get it to move. So what's happening is basically the pressure on the left side has to equal the pressure on the right side. But pressure is force over area. So I'll call the left side 1 and the right side 2. So the ratio of force per area is the same. The bigger area required a bigger force to get it to move. The smaller area only needed a smaller force to get it to move. Now, to relate it in terms of distance, that goes into work. The work I did pushing on one side is equal to the work done moving the other side. Remember, work is force times distance. So for a bigger force, you'll get a smaller distance. A smaller force, you'll get a bigger distance. And that's why that smaller syringe moved farther, because the force was smaller. Yes?
What about, I mean, you can do it with volume as well.
Yeah. If we take these, for example, if we solve this one for F1 over F2, we'll get A1 over A2. If we solve this one for force 1 over force 2, we'll get D2 over D1. If we set these equal to each other, A1 over A2 equal to D2 over D1. Get the ones on the same side. Area times distance is volume. So exactly right. Volume 1 that moved has to equal the volume 2 that moves on the other side. Exactly right. So these equations show that that volume works as well.